Hello, this is Tracy. Welcome back to Math 135, Introduction to Statistics. This will be the last video lecture for Chapter 3, our topics and probability. And we are going to start by looking at contingency tables. And these are just tables where we gather together our information so that we can see it in a more visual way. So here I've taken data from information from another text, and we have a survey, the results of a survey of subjects who either received a speeding ticket in the past year or they didn't, and the color of their car. So when we look at our table, we can see we've got our speeding tickets here, and we have 15 people who had red cars and got a speeding ticket. Of people with a speeding ticket, 45 did not have a red car, and a total of 60 people got speeding tickets altogether. In our next column, what we have is we have all the people who did not get speeding tickets and whether or not they had a red car. So, no speeding tickets. 135 of those without speeding tickets had a red car. 470 of those without speeding tickets did not have a red car, and 605 people did not get speeding tickets. In the last column, we have the totals for how many people had red cars. Red cars, we had the 15 with speeding tickets, plus the 135 without speeding tickets. 150 people had red cars. The grand total number of people who did not have red cars: 45 who got speeding tickets, 470 who didn't, for a total of 515 without red cars. And our grand total here is 665 people in our survey. You can get that two ways. Adding up here the people with red cars and the people without red cars gives you 665, or the people with speeding tickets and the people without speeding tickets adds up to 665. Okay, now we're going to use this information and calculate some probabilities. So what's the probability a randomly chosen person has a red car? We are going to do this using the experimental probabilities we have determined. We surveyed 665 people. And out of those 665 people, how many had red cars? 150 total. So we're going to go here and talk about the probability of having a red car is 150 out of 665. Now, the next thing we're going to ask, what's the probability that a randomly chosen person does not have a red car? So there are two ways we can do this. We could say the probability that the car was not red is 1 minus that 150 over 665. Or we can just look up at our table and say how many people don't have red cars out of the number of people that we have in total. Either way, that answer is 515 out of 665. Now, what's the probability that a randomly chosen person got a speeding ticket? So again, we're going to look at our table and we're going to say, all right, how many randomly chosen people do we have? 665. So the probability the randomly chosen person got a speeding ticket still going to be out of that 665. And we look at our table and say, ooh, 60 of these people got speeding tickets. So there's our probability that a randomly chosen person got a speeding ticket. What's the probability a randomly chosen person did not get a speeding ticket? And again, two ways we can do this. Just like the probability randomly chosen person doesn't have a red car, we could either look at this as the complement, probability a randomly chosen person did not get a speeding ticket, 1 minus 60 out of 665. Or we look at our table and we say, ooh, how many people did not get speeding tickets? However you do it, you're going to get 605 out of 665. So let's go write that down. 605 out of 665. Sorry, it looks like I didn't leave enough space for all of these questions with the table in view. What's the probability a randomly chosen person had a red car and got a speeding ticket? Red car and a speeding ticket. Now, these events that we're looking at are not necessarily independent. So we can't just go using that cool multiplication rule that we had before. We can't just multiply these probabilities together. What we need to do is we need to look at our table, and from our table, figure out how many people had a speeding ticket and a red car. And that's going to be this right here. 15 people both had a speeding ticket and a red car. So the probability a randomly chosen person has a speeding ticket and a red car, probability of a red car and a speeding ticket is going to be that 15 out of 665. Now, if we want the probability that a randomly chosen person had a red car or a speeding ticket, probability of a red car or a speeding ticket. Here, we don't need our events to be independent to use our addition rule. Here, we can just use that addition rule and say, well, that's the probability of a red car plus the probability of a ticket minus the probability that they had both red car and a ticket. That's an and. Sorry, I'm running out of space. Okay, so let's do that. What was the probability somebody had a red car? Well, that was 150 out of 665. The probability somebody got a ticket was 60 out of 665. But we are double counting those people who had both. Those people who have both a red car and got a ticket got counted in the red car group and counted in the ticket group. So we got to subtract them off. Minus 15 over 665. So 150 plus 60 is 210. Minus 15, this is going to be, I'm running out of space. Sorry, folks. No, I can't just add more space to it. Okay, it's going to be 195 divided by 665. There's our answer. That's the probability somebody either had a red car or got a speeding ticket. Now we can also figure this out by looking here at our table. Let's get rid of all this other stuff I've circled. The probability that somebody either had a red car or got a speeding ticket, well, we look at the people who got speeding tickets. We look at the people who had red cars. If we add all these together, we are still going to wind up with 15 plus 135 plus 45, all out of our grand total of 665 people. And this still gives us 195 out of 665. And again, that's the probability of a red car or a speeding ticket. Two different ways, both get us the same result. We can feel pretty good about that. All right. Now, we were looking way back at independent events, but sometimes events are not independent. We would have seen that up above had we tried to multiply the probability of a red car times the probability of getting a ticket. You'd find out you don't get the same answer as we did by looking through our table. sometimes the probability of one event does depend on the results of another event, and that's what we call a conditional probability. So we want to figure out the probability that two cards drawn from a deck of cards will both be aces. Assume that we do not put that first card back. So the probability that your first card is an ace. Well, there are 4 aces out of 52 cards. That's the probability that our first card is going to be an ace. Now, we can multiply that by the probability our second card is an ace. But it's not going to be just 4 out of 52, because once you pull that first ace, you only have 3 aces left. Once you pull that first card, you only have 51 cards left. So the probability that you draw 2 aces is the probability that your first card is an ace times the probability your second card is an ace, assuming you already got that first ace. So that's going to be 12 out of 2,652. This that we just calculated is called the conditional probability. It's the probability that the event occurs. Yeah, it's the probability of B, and that little line there means given that A occurred. Probability of B given that A occurred. And that gives us another multiplication rule. And that multiplication rule says that if events A and B are not independent, is times the probability the second occurs, given that the first already happened. So that's here our 4 out of 52. That's the probability that we get that first ace. And this is the probability that we get that second ace, given that we already picked an ace out of the deck. Okay, so we're going to look back at that table that we had, and we're going to find a couple of different conditional probabilities. What is the probability that a randomly chosen person had a red car, given that he or she received a speeding ticket? What is the probability that a person chosen at random has a red car, given that he or she has a speeding ticket? So this given that piece right here, this is our denominator. These are all the people we are looking at. We know this person had a ticket. So all we're looking at out of this table up here is the people who had tickets. Now, of those people who had tickets, how many of them had red cars? So this is where we get our numerator. The number with red cars of those with tickets. And that's going to be this 15 right here. The probability that somebody has a red car, given that they have a speeding ticket, is those who have red cars out of the speeding ticket group. 15 out of 60. Now let's look at number 2. It is not the same problem. It's very similar, but it is not exactly the same thing. Here we're looking at the probability that a randomly chosen person got a speeding ticket, given that they had a red car. If you know somebody has a red car, that's your denominator, the people with red cars. Actually, let's change the color. Red. All right. So we want to look at the people who had red cars. 150 of those. There's our red cars. Now, of those with red cars, how many got tickets? Let's make our tickets black. Of those 150, how many had tickets? Well, still there's that 15. Oh, we don't need to reduce that, sorry. Old habits. I like reducing everything. Although what we could do that might make things helpful is we could turn these into percentages. So 15 out of 60. You divide that, you get 0.25. Put that in your calculator. And we could turn that into a percent. 25% of people with tickets had red cars. Of those with red cars, 10% of people with red cars got tickets. 25% of people who got tickets had red cars. These are different things. And that leads to a pretty important thing to notice here, which is that our conditional probabilities, the probability of A given B, is in general not equal to the probability of B given A. What we know, what our denominator is, makes a big difference. And that leads us to another contingency table, another problem taken from a different statistics textbook. And here we're talking about pregnancy testing. So we have this table, and these show us the results of a home pregnancy test. So you've got the results of your test. Your test can be either positive or negative. And then you go to the doctor takes blood tests, and they say, okay, what's really going on? And the blood tests determine if you're actually pregnant or not pregnant. That's more comprehensive than the home pregnancy test. So we want to look here at the probability that you get a negative test result given that you're pregnant. Given that you're pregnant. And this is your denominator. So how many people are actually pregnant? Pregnant, the total is 74. 74 people, women, I assume women, no point in getting a home pregnancy test if you're a fella. So 74 women are actually pregnant. How many of those got negative test results? 4. That's not too many. You know, if you're not, or if you are pregnant, it's not very often you get a false negative, a result that says you're really not when you actually are. But now let's take a look at this other conditional probability. Here, all we know is you got a negative test result. Given that you got a negative test result, this is your denominator. Well, how many women got negative test results? Grand total with a negative test was 18. So 18 women got negative test results. How many of those women were actually pregnant? Oh. Negative test result, 4 of them were still actually pregnant. Let's actually, I haven't done this yet, but let's actually put this in the calculator and get some percentages. The percentage of pregnant women who got negative test results is about 5.4%. Tiny percentage of pregnant women got the wrong result. But 4 out of 18, out of all those women who got negative test results, 22.2% of them said, whew, I'm not pregnant. What a relief. And then they got a blood test. And 1/5, between a fifth and a quarter of them, the result was, just kidding, yeah, you are pregnant. So, conditional probabilities, what you're given, what you know, makes a big difference. Here, this is the relevant probability. This is what you know, the result that you get. It takes further testing to figure out if you're actually pregnant or not. All right, so this is the end of our Chapter 3 lecture notes, and we'll be moving on to Chapter 4. As always, please let me know if you have any